Okay, hi everyone, and welcome to our week 6 material. So today I would like to talk about the non-destructive tests as opposed to the destructive tests that we talked about them last week, and we'll see what is the difference between non-destructive and destructive tests, and what are the different types of or examples of the non-destructive tests. As I just mentioned before I start about the term paper, it will be next week. So it is like regular time here. I will have the list of all the names. I will randomly select any name. Then you can, guys, you can just basically share your presentation, and you start your presentation, 8 minutes, followed by 2 minutes discussion, and that's it. So it's I'd like to make it simple. No need to go more than that. Any concerns about the term paper before I start? Okay, good. So non-destructive test. What is non-destructive test and how is different than the destructive test? The destructive test that we mentioned, either over voltage test or impulse tests, either switching or lightning tests, they are pass and fail tests, meaning that the outcome of the test that the asset has passed the test or has failed the test. That's it. But non-destructive tests, on the other hand, they give you information about the quality of the insulation. So it will tell you if the insulation is good, excellent, moderate, bad. So you will have more of descriptive terminologies or descriptive words to describe the insulation. Is it aged? Is it still new? Does it have moisture in it? And so on and so forth. So these tests are for the quality of the insulation. And the most common ones is the insulation resistant tests, or we will call it the MEGAR test, as we will see. Polarization index, which is somehow a measurement that we do during the insulation resistance test. Then we have the dielectric loss capacitance and visual corona, and finally the partial discharge. So I will talk about the insulation resistance. I will talk about the polarization index. I will talk about dielectric loss and about the partial discharge. These are the most common ones. Now, these tests are conducted in the factory and in the field. My concentration more talking about in the factories, but you will see a little bit of overlap, especially for dielectric loss or insulation resistance. Some you will see that some of the what I mentioned could be applied to the field as well. But for the partial discharge, I make it only restricted to lab tests, meaning that when you do the test in the lab under controlled conditions, because partial discharge can be conducted in the lab or can be conducted in the field. But when you conduct it in the field, you use totally different instrumentation, not the same instrumentation as we use in the lab. And we'll talk about field testing next after we finish the term paper, and we'll talk about what are the online techniques that we use partial discharge, or what are the online partial discharge measurement systems that we will have. So we'll start with the insulation resistance and the polarization index. So from its name, you are trying to measure the resistance of an insulation. As we know, material are basically can be classified as conductors, as dielectric or insulation, or semiconductor. And the reason of this category, or why we have a conductor, why we have an insulation, it depends on the number of electrons in the valence band. So if you have 1 to 3 electrons in the valence band, these are conductors, because those electrons can be easily detached from the atom and leading to the conduction of electricity. On the other hand, dielectric materials has much higher number of electrons, 7 at the outer or at the valence band. Hence, they cannot be easily detached. So the current, the movement of electrons, theoretically is zero. There is no current going through an insulating materials, meaning that the resistance is infinity. But practically, that's not the case. Practically, we have a finite resistance. Now, one of the most common tests that we use for the insulation resistance qualifications is the Megar test. And in the Megar test, basically here, this is two different examples. We'll talk about it in a bit in more details. In this example, basically here you'll see a sample. Okay, so you have here a conductor, and here you have an insulation, and you are applying a high voltage between the conductor. This is the line between the conductor and the insulation. So you are testing the insulation between these conductors, these two. Or here you see the same thing. You have a cable, and you're applying the high voltage between two conductors to measure the insulation between these conductors. So basically, you are trying to measure the DC resistance. So in both cases, you apply high DC voltage. So Megar is done through DC voltage, not an AC voltage between the conductor and the ground. Between the conductor and the ground, there will be always an insulation. So you want to see the quality of that insulation. And using simple Ohm's law, the insulation resistance is equal to V, the voltage that you apply, divided by the current. Now, in some devices, it shows you the current. In some devices, it will show you the resistance right away. Now, here the characteristic of that current or the insulation resistance, because it is basically they are both inversely proportional, they are not constant. What does this mean? If I have a small resistance, a regular resistance R, and I apply a DC voltage here to it, V, and I measure I, your I will equal to V divided by R, or your R is equal to V by I. It's constant value. It doesn't change with time. But here, when you connect the Megar test, you will notice that the value of the current is not constant. As a matter of fact, it decreases with time, and hence the value, so this is decreases with time, the value of the insulation resistance increases with time. And we want to understand why this is happening. We'll talk about that in the coming slide. So basically, there are different currents that goes through the dielectric materials. Some of them increase and stabilize. Some of them start to decrease. And the overall current will be basically decreasing. And we will understand what are those currents and why this is basically happening in the insulation system. So here we have three different currents. We have the capacitance or charging current. Start with a very high value. So this is the x-axis is the time, and the y-axis is the current in microamps. So the current start is a very high value and then goes almost to zero. Another current in red is the absorption current, also start as a high value and also reduced. Then we have the conduction current or the leakage current. This is start as zero and then start to increase and then stabilizes with time. It doesn't change with time. Then this is your total current. So the current starts with a high value and start to go down. And then if you extend this, you will start to stabilize. So hence, once the current starts to stabilize, then the insulation resistance will stabilize as well. Now let's try to understand what are those currents. Why those currents start as a high value and then start to basically to reduce. So we'll talk about these three currents: the capacitance currents, the absorption current, and the conduction current. And we want to see which one is really reflecting the insulation resistance. So the first current is called the capacitance current. This is because you apply basically, you have a conductor here. This is one conductor, and here's another conductor. One of them is supposed to be the high voltage, and the other one is the ground. So you connect basically your Megar test or your insulation resistance test between these two terminals. Okay, so you apply here high voltage, and here is grounded. Okay, so you have conductor here, conductor there, and in between there is the electrical insulation. So that is a capacitor. So when you apply the high voltage, you are basically charging a capacitor. And going back to the circuit theory, the capacitors, when you connect the high voltage DC to it, it starts as a short circuit and then it evolves as an open circuit. So that is from the simple circuit theory. Capacitor, when you start, basically, when you start charging it, start as a short circuit, means a short circuit, you will have a spike, a very high current to start with, and then this current start to die until it becomes zero when you have your capacitor is fully charged. So that is this is actually no exception. The cable, the insulation system is nothing but a capacitor. So when you apply the DC, you will start charging that capacitor, regardless what is the configuration of that capacitor. And then after that, it will dies out when you are fully charging your installation system. Then we have the absorption current, which is also somehow has a relationship with the charging. Now, you have in the dielectric materials dipoles. Now, those dipoles, due to the application of the high voltage, they are orienting themselves. The energy that's spent, that is actually the absorption current. When you start to align them, eventually, so they are first, they are random, and then they will start to align with the electric field. Now, once you start to align, the current start to decline. So the current start is the energy spent to align those dipoles until they are fully basically aligned. So these two currents eventually dies to a very, very small value. And these two currents has nothing to do with the quality of the insulation. These are because of the nature of the insulation system. It's a capacitor. They are having dipoles. So it has to go through this process. So this is why when you apply the insulation resistance, you cannot just apply the voltage and take the value. You have to wait. And usually we wait around a few seconds, sometimes 10 seconds, sometimes 1 minute, sometimes 30 seconds, and then we take the measurement. Why we are doing this? Because we are waiting for these two currents, which are not a reflection of the quality of the insulation, to die out. Finally, we have the leakage current. Now, the leakage current is basically, or the conduction current, that is the current that I am interested in. That is the current that basically reflects the quality of the insulation that is done by this current. And when you see here, this current stabilizes with time. So start to increase, and then it stabilizes and stays, okay? And that is the current that is basically, that you want this current to be equal to zero, okay? It's not equal to zero, but you want it to be equal to zero because you want to have an insulation as an infinite resistance, which is not the case. So it reflects the higher the current, the bad is the insulation system, and vice versa. So that is the insulation resistance. Now, to avoid some confusion about the results, because as you see here, it depends on the configuration of the system. Basically, you will have different values and times for the fully charging. We will come up with the polarization index. The polarization index is basically the division of, and this is one of them, or this is one of the most common formula. It's a division between the resistance after 10 minutes to the resistance after 1 minute. So the polarization index is R10 divided by R1. Okay, so that is your polarization index. Now, what we expect to see here, okay, now let's think about it. You start the current as a very, very high value, and then this current start to decline so that your resistance will start to increase. Okay, so the current decrease, the resistance increase as well. Okay, so you expect that the resistance after 10 minutes basically will be higher than the resistance after 1 minute. So the polarization index, you expect that to have a ratio over 1, more than 1. And that is an indication of a good insulation system. Now, if this is lower than 1, then it means that as you apply the voltage, your resistance is decreasing. This happens only when you have bad insulation systems. So uh, that is how we can interpret the results. So PI less than 1, this is meaning that the windings are wet or contaminated or bad. If the PI is greater than 2, then it's a clean and it's a dry, it's a good insulation system. As we will see that the polarization index and the Megar test, we use it for different applications. We sometimes we do, as I will mention, some manufacturing process, and you want to see the quality of that process specifically, we use the Megar test. And sometimes we use it to evaluate the insulation of the system and the field as well. We want to see what is the polarization index or the insulation resistance of the equipment and the field. Now that will be very helpful if you have the history of this specific asset, so that you know how much is basically the value, how much the value was, and then you will tell if there is any deterioration happening. And the IEEE 430 by 2000 is the guide discussion about the insulation resistance and the polarization index. So let me give you some specific example that we use the IR, the insulation resistance and the polarization index. So one of them is basically to measure the or evaluate the insulation of a rotating machine for the motors and the generators. That is widely commonly used to evaluate how good or how bad is the insulation resistance of the motors and the generators. And basically you apply the high voltage between the copper conductors and the core. If you want to see, for example, the core insulation systems, because there is an insulation systems between the core and the your conductors. Okay, so if you want to see how good or how bad the system, we try here to measure the this resistance. Ideally, you want it to be infinity. There's nothing called infinity here. So basically, it is giga-ohm is what you are looking for. That is a good insulation system. Another application of the Megar test and the polarization index is to check the dryness of the transformer. Now, when we manufacture the transformer, basically after we finish the winding, we have the low voltage winding. Let me talk about distribution transformer, for instance. So we have the low voltage winding, then we wind on top of it the high voltage winding, then we put the basically we have the core. Talk about core type transformers. Let me talk about this. For example, you have the 3-leg core of the transformer here. So this is, you assemble them. These are by assembly. So this is the core of the transformer, and then you stack them basically until you get the required cross-section area, and then you install on top of each one, you install the winding, the 3 windings, which is basically composed of the high voltage and the low voltage winding. Okay, and then you come and you close the top part of the transformer by adding the final magnetic material. So then you will have this is your 3 windings here. So this is one winding, this is another winding, and this is the third winding, and you have the core material is completely this is a 3-leg transformer. So when you energize the transformer, you have the flux going through this. Now we call all of this the active part. Now in this active part, because you do it in the factory, there's humidity, then the insulation system will basically absorb part of this humidity. Also, we use the insulation paper between turns. We use a specific material, and that material has a glue in diamond shape. So each the paper, if you look to the paper, you will have them having those diamond shape of glue, and that glue will be activated at very high temperature. So we call this is the active part, because this is basically the part where you have the induced voltages, the flux, the current, everything is done through this. The rest of the transformer it's not active. There is no energization. The other part of the transformer for protection, for cooling, when it comes to the oil and so on and so forth. So we need to get rid of the moisture. Now, based on the size of the transformer, we have to put it inside an oven. Now, how to test if the transformer basically has been dried well? Okay, because if the transformer is not dried, it means that their insulation paper still has some moisture, and that on the long term is really bad. Remember, the IR and the PI are tests to evaluate actually the quality of the insulation system. So we apply the Megar test there, apply between high voltage to ground, low voltage to ground, high voltage to low voltage. We measure all these three resistances. Typically, we apply around 5 kilovolt DC for the high voltage and 2.5 and sometimes 1 kV for the low voltage. And the insulation resistance should be in the giga ohm resistance. Okay, so if, for example, the oven is not working properly, maybe the humidity level inside the factory is extremely high, then you will see a low value, something that's not typical. And that's why it's extremely important to measure the insulation resistance after the drying of your winding of the transformer. Also, another application, but this is maybe more done in the field, is to measure the health condition of the transformer bushing. As you know, at the high voltage, especially at the high voltage side, we have the bushing. The bushing is a hollow insulator through which you have the conductors. And because this is work under outdoor conditions, it ages with time. It might absorb certain moisture. On its surface, there is a lot of dirt. So you want to see what is basically the insulation resistance of that bushing, especially if you know the initial value, and if you see if that you want to see if the bushing basically has been deteriorated with time. So you need to apply the high voltage DC Megar test to measure the insulation resistance. But you have to make sure that you do the test at a dry and a clean weather, because if there is a lot of moisture, basically, then you will not measure the bulk of the insulation resistance, but you will measure the surface resistance. The surface resistance will be affected by the moisture. If there's a lot of moisture on the surface and you apply the high voltage, then you will start to have a surface current. That surface current does not really reflect, that's not the current that you want to measure. You want to measure the current that go through the insulation, not at the surface of the insulation. Let me explain this is more. So if this is the bushing, okay, that you want to measure its resistance or insulation resistance, and in between here we have here the conductor here. The conductor is going, this is the tank of the transformer, so the conductor is going through the bushing. So it's a hollow insulation system, okay? So I want to measure between the high voltage, this is the high voltage here, and between the connected ground here. So I want to see the current that goes through here, through the bushing itself. So that is reflecting the quality of the insulation of the bushing. However, if the surface is moist, then you start to have a current on the surface would be misled, okay? And hence, the surface has to be dry, it has to be clean, so that you will not have any surface current, rather than you will have only bulk current to be able to measure the quality of the insulation of the bushing. Also, we try to make the terminals as short as possible to minimize any error coming from the measurement. As I said, that's a very good test, especially if you have the results from the manufacturer. So you have something to refer to and to tell you if the quality of the bushing has been deteriorated or not. Now the test can take 15 seconds, 60 seconds, 180 seconds, or 600 seconds. The most important thing that it doesn't matter what is the amount of time, as far as when you compare your reference should be being conducted at exactly the same time, so that the comparison is really fair. As now we understand why we need to wait that time, because we have to wait until the current start to dies out and become negligible compared to the leakage or the conduction current. So that's enough about insulation resistance and polarization index. Now, I will talk about another measurement, which is called the dissipation factor or the power factor. Okay, dissipation factor, and we'll see that in
So
our
yeah, I
next.
have a question. Uh,
Yes, go ahead, please.
can you go back to the previous slide? So the readings that would be taken at the 15 seconds, 60 seconds, that would still be considered conductive current, or would that be past the capacitive
Now,
slash
okay,
absorption?
okay, very good. Now it depends. It depends basically on the. Now these times depends on the size of the bushing. If you have a large bushing, then you need maybe to wait at longer time. But
Mm,
if you have a smaller bushing, then 15 seconds will be enough for the because the capacitance of the bushing itself is small if you have a small bushing. So it would the current will die out very fast.
mm-hmm.
Okay.
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 Yes. Thank you.
Okay. Okay. Now let's talk about the now when it comes to the transformer dryness, we usually take around 1 minute to wait because I am basically measuring the insulation resistance of the whole winding. That is a huge capacitor. So you have to wait for 1 full minute until the capacitive current dies out. For a bushing, it is much less. Now, if you have power transformer, the bushing is huge. Then you have to wait more time. The second test is the dissipation factor, sometimes called the dielectric loss factor or the power factor. They are different names. They are a bit different, but at the end of the day, they are very close values. Now, for a perfect insulating material, it is basically represented as a capacitor. Now we know from the Meggers test that's not correct. Because if it is only a capacitor, if it's only a pure capacitor, then the resistance will be infinity because the charging current, the absorption current will die out. There is no current. So current becomes equal to zero. If the current becomes equal to zero, then you will have an infinite resistance. But we notice now, no, there is another current, a third current, which is the leakage current. That is the current that is basically only, it's a resistive current. Okay, so in practically, you can represent the resistance and the dielectric material or the insulating material as either a resistance in parallel with the capacitor or a resistance in series with the capacitor. There are two different models. We will see both of them here. Okay, so this resistance part, this is the model. This is the model actually of the insulating materials. So when you apply a voltage across this insulating material, then you will have to count. Now, this voltage that we use for this test is an AC voltage, not DC. In the Megger, in the polarization index, it is basically uh, it is a DC. Here it is an AC. Okay. Now, if it's an AC, then the capacitor will be modeled as 1 over omega C. ZC will equal to this value. Okay. Now, you apply the voltage, you have the total current I here. This is the total current. You will have two components. You will have IC and you will have IR. IR is the resistive part of the current, and IC is the capacitive current. Okay. Now, what is the definition of the tan delta? Tan delta basically is the ratio of IR divided by IC. That is the definition of the tan delta. Now, we will not be able to measure that current. It's very difficult to measure. This is we'll see how we will measure the tan delta practically. But basically, what does this actually represent? Now, when you look to IR, this is a simple circuit model. Your IR is nothing but the voltage divided by RP. That is your IR. IC, on the other hand, is the voltage divided by the impedance of the capacitor, which is 1 over omega Cp. So now take the ratio. IR is V divided by RP divided by the voltage V divided by 1 over omega Cp. So when you do that, this will cancel, and then you will have your tan delta is equal to 1 over omega Rb times Cb. That is the definition of your tan delta. Tan delta is called the dissipation factor. we have also, along with that, we have the power factor. Power factor, as any power factor, it is the resistive part divided by the whole current, which is equal to this. Now, tan delta is equal to delta when the angle is very, very small. And as a matter of fact, when the current is when the angle is very, very small, the dissipation factor and the power factor, both of them will be equal because I, it is basically mainly IC because the resistive current is extremely small. The main current that you have is IC, not IR. IR component is very, very small. So that is the theoretical meaning of the tan delta, the power factor, or the dissipation factor. Let's see how we do the measurement here. We use what we call the shearing bridge. Now, what is a bridge? Let's just talk about it generally speaking. What is a bridge? A bridge, like for example, the Wheatstone bridge, it's the same principle. In a Wheatstone bridge, we use that bridge to measure unknown resistors. We use it, for example, in the context of measurement to measure the change of the resistance, for example, in a sensor. So the bridge, for example, the Wheatstone bridge here, and as we said, the same principle applies. You apply a voltage here to it, let's say Vs. We have here R1, R2, R3, and R4, and you measure your V out. Now, if the bridge is balanced, your V out is equal to 0. Now, how we can use this in our advantage? For example, let's say that R3 and R4. So if balance means R1 over R2 equal to R3 over R4. If this happens in a bridge, if R1 over R2 equal to R3 over R4, we say that this is a balanced bridge. The bridge is balanced, and your V out will be equal to 0. And the current that goes here is equal to 0, even if you connect a resistance. Okay, so that is basically the definition of a balanced bridge. Now, how we can use this information to help us to find an unknown resistance? How we do that? You connect that R3 and R4 are known resistors. So I know that leg, this ratio. R2 is basically as unknown resistance, for example. This is something I want to measure. And R1 is basically a variable resistance, something I can control. Okay, so I bring that resistance here. Most likely the system is not balanced. R1 over R2, which you don't know, is not equal to R3 and R4. This is a random resistance that you have no value. So then you start to play with R1. You start changing R1 until you make the bridge balanced. Once it's balanced, you know now V out equal to 0. It's a balanced bridge. Then R1 over R2 will equal to R3 and over R4. R1 is the controlled resistance, so I know its value. R3, I know its value. R4, I know its value. Then R2, the only unknown, I can find its value. So basically, this is one method that we use to precisely know the resistance of unknown resistance. Same thing here for the shearing bridge. It is composed of the following. We have here a Cn. Now here, because our system is not just basically resistance, it is capacitive and resistance. Now we understand from the previous slide that the best model for our insulation system is a resistance and a capacitor. Okay, so now I need to find both values. Then we have to connect it to an AC system, not to a DC system. Now Cn here, which is here, is a standard measuring capacitor. So that is a capacitor that I know its value. Rx and Cx are the series representation of the power system component. So that leg of the bridge represents what? Represents the insulating material. As I said, you could have R and C in parallel or in series. You have both representations. Here we are using the series representation. R3 and C4, R3 and C4, these are two variable resistors and variable capacitor. We control them until the current in the galvanometer. A galvanometer is a very precise meter that can measure current, very, very small values, and be measured using the galvanometer. Okay, so we keep playing with this until the reading in the galvanometer is basically is equal to 0. Then that is the balance condition. And once the balance condition, it happens when the tan delta, which is basically equal to omega Rx Cx, will be equal to, now this is, I don't know Rx, I don't know Cx. All I have is an insulating material. But I know C4 and I know R4. I know these two values. So I'm balancing this leg of the bridge with this. Then your tan delta, which is basically equal to omega Rx Cx, that is the actual value. It is also equal to C4R4, which is basically the value that I am using to control, a value I can find. Then I can find the tan delta. I will try to have one video. We have the system set up here. We have both the IR, the insulation resistance, as well as we have the tan delta. So I will try to do some demonstration to you to show the physical system, how they look like, and I will post that video. I will need the help of Abdullah. Abdullah is going to a conference next week, so maybe after he come back, I will try to arrange a video for this. Now, usually the tan delta or the dissipation factor is a test that you do it when your equipment is new. Okay? And when the manufacturer ship the equipment to you, it's good to do it when you receive it. Because if there is any damage happens, that will be easily detected. If any damage happened in the insulation system during the shipment, like for example, transformer, especially the power transformer, it's trivial. It's shipment. It is basically a huge mass and goes for long distances. So something can happen, some vibration can happen, damage the insulation system. So doing the tan delta at site, this is one of the tests, also can be done at the site as well. And the same principle, it's exactly the same principle. We have portable devices, we can do that at the site. Then you can compare between what has been done and during the shipment. Also, you can tell about the insulation quality as a function of aging. When the insulation system ages with time, then you can see that in the results as well. So you can compare. For example, you have the equipment now 10 years inside. You know initially what is the value, maybe every other year or every year. You take the measurement, you have the history of that. So then you will see what is going on with the tan delta. Of course, it's needless to say that you want to have the tan delta as very, very small value. So now, if it is increasing, meaning that either there is a moisture absorption in the system or there is a deterioration of the insulating material. Okay, so that is basically it. The tan delta can be used to measure that. The tan delta is a bit better test than the insulation resistance. Insulation resistance is something I would say very primitive. It is good, but and give you some indication. But the tan delta is more precise. Being in the bridge gives you a very precise, nice results. Now, if we have newly filled transformers or reactors, the power dissipation factor is less than 0.5% at 20 degrees centigrade. Now, as transformer age with time, as I said, the value can increase, and this can be, for example, it could be an indication of insulation resistance, the transformer, because as transformer, and we see that we talk about field testing, as a transformer age in the field, transformer, it will start to absorb moisture, okay? And the water content in oil and the water content in the insulation will start to increase. So the tan delta is a very good measurement to tell you if how much, relatively speaking, how much is the increase in the moisture content in the insulation system of your transformer, or if there is contamination, or there is, because again we will learn that we'll talk about transformer oil after the break, that there are certain measurements like the acidity, like the interfacial tension, the dissolved gas analysis. These are all contaminations will be added or can be reflected in these measurements because of electrochemical reactions that happens in between the cellulose paper, the high field, the oil. There is some arcing whenever there's any short circuit or partial discharge. Then hydrocarbon will start to be released. This will increase the contamination. More conductive material you'll see in the oil. Now, these conductive material, these contaminations can basically be detected using the tan delta. Now, this is a very interesting, nice example of a bushing. Okay, so we have 4 bushings, A, B, C, and D. Let's try to understand what is the meaning. So here we have the x-axis is the voltage that you apply. This is the voltage per, this is divided by root 3 to find the phase voltage. So this is the line-to-line voltage. This is the phase voltage of your equipment. And here is the power factor or the tan delta. This is the value of that. Okay, so we'll start with bushing A. This means it's a very good one. Okay? So you increase the voltage, you exceed the rated value, nothing happens. Now, once you start to increase higher than the rated value, you see there's a little bit of increase in the power factor. That is healthy. So that is normal because you increase the stress higher than the rated value. So that should be okay. Now, when you go in bushing B here, now before you reach to the rated value or the phase voltage, there is a tip up. There is a sudden increase to the voltage, means that there is a defect in that bushing. Means that that bushing basically has somehow some defect somewhere, and when you reach that level, there is jump in the conduction current, meaning that the IR current has increased significantly, and this will lead to the sudden increase in the dissipation factor. Now, when you go to the C here, it behaves like the A somehow. Okay, so it's consistent. It does not increase with voltages except when you exceed the voltage. However, the value here is consistently higher. That is an indication of moisture. So always you have to have a sort of something to compare with. You cannot just basically have an absolute value. It depends on the system and the environment and so on and so forth. Finally, bushing D, this starts with a very high value and then start to drop. That is an indication that there is a defect in the aluminum foil. Okay, so that is basically because of the damage happening, there is a change in our modification of the electrical stress, which will resolve. So you start at a high value and start to drop. That is not normal. The normal, you start at a low value, and then when you exceed the voltage, you start to increase. When it does the opposite, it means that there is an indication of aluminum foil. Aluminum foil, this is one of the stress grading methods that we mentioned, that we have it in the bushings. Any question? Okay, so I will pause for, let's say, 6 minutes. Let's have a short break, and then I will come and talk about the partial discharge. Okay, now we talk about the partial discharge, and I will limit my discussion to the laboratory measurement, that when we use the partial discharge under control, under a factory, at the premises of the factory, we will see later on how we do the partial discharge at a different place. Okay. Now, many times the failure of the insulation system is due to the presence of a partial discharge. Now, these partial discharge, basically, when you have, let's say, if this is, let's talk about a very simple system. You have here a small void. Here is your high voltage. Here is your ground. Here you will have a very high electrical stress inside this void. And the reason for that, why we have an enhancement in the field here inside the air voids, in the insulation system inside it, because basically you will have here an electric field, and the electric field is basically follow the flow of the electric field between different materials. This is dielectric material or insulation. This is here. We have here an insulation. Here we have air. Okay, so epsilon 1 E1 is equal to epsilon 2 E2. So at the interface between the insulating materials and air, you will have this relationship that governs the flow of the electric field. Now, in air, epsilon is equal to 1. In the electric material, it's 3 to 5. Okay, so it means that the electric field inside the air void is larger than the electric field in the insulating material. Second, the breakdown of air is much less than the breakdown of the dielectric material or the solid insulation material or even the oil insulation material. So this is what result in a partial discharge inside this void. A localized arcing. Partial discharge, it means it is a localized arcing inside this void. An arc does not bridge the high voltage to the ground. It's not a fault. It's just partial discharge. Now, this partial discharge will take weeks, will take months, years. It depends on the intensity of the discharge. Then the void would start to expand until you have a complete failure happening to the installation. So many times the presence of the partial discharge is basically the root cause of installation failures. I always give the analogy of partial discharge as cancer. Cancer starts very small, very confined in one place, but if you don't detect it at an early stage, it starts to propagate until the human body damages the whole human body. Now, in the partial discharge at the factory, the best way is to detect it at the factory. If there is any fault happened or any weaknesses in the system, you need to detect that basically at the factory, and you do that test for cables, transformers, insulators, and so on and so forth. Sometimes the partial discharge develops in the site because of the aging, because of the stress, because we have different stresses in the field. So it basically it can be caused not because of manufacturing defect, but because of aging that happens in the site. So you need to measure the partial discharge also frequently in the site as well. As I said today, I will talk about the partial discharge measurement system in the factory. Later on, we'll talk about the partial discharge measurement in the field. So again, to reiterate what I mentioned, the partial discharge is a localized electrical discharge, no complete bridging between the high voltage and the ground. So it's partially bridges the two conductors. There's some subcategory of that, we call it corona. Corona basically when the discharge happening around the conductor is not in contact with the electrical insulation, we call this as a corona. For example, overhead lines, the conductors, the discharge around the overhead conductors, this is not called partial discharge, but we give it the name of corona. Corona, I think it's a Greek name or Latin, I'm not sure, Greek or Latin. It means that in the early morning when you look to the sun, around the sun, there is sort of a small circle around it. That is called corona, which is basically represent what is the meaning of the corona. Now, the partial discharge can be, as I said, internal defects. This is a cavity inside. For example, epoxy material due to the manufacturing process. This is an electrical tree. This is a cross-section area of a cable. Electrical tree is one of the major causes of faults in cables. Now, you could have that as a surface discharge. For example, here, this is a conductor. There is no electrical insulation at all involved. This is called corona. Now, if there is a high voltage, it's external, not internal, but there is a surface discharge happening, then this is called surface discharge and not corona. For example, in ceramic insulators, at the cap and the insulation here, so this is the ceramic shell, This is the cap, and this is the ceramic. This point, this is air. This is considered as highly stressed region. So you could have some sort of partial discharge on the surface. We call it surface discharge. Now, how to understand the partial discharge model? How we can use that model to understand the phenomena of partial discharge. So that is a very famous, they call the capacitive equivalent circuit for a partial discharge. So let's try to understand what is this. So this is, imagine we have this system. This is a high voltage, and there is an earth electrode, and this is an air void. So this is your air void, which is a defect. So the whole system here is a good system, but this is an air void. Okay. Now, how to represent? We represent the whole good system as basically capacitance CA. Okay. So CA represent the capacitance of the rest of the insulation. Now, CB represent the capacitance of the insulation system above and below the air void. So this is your CB. And CC is basically represent the capacitance of the air void. So we have like two capacitors in parallel. When you apply the high voltage, each one, because of these two parallel branches, the electrical stress on that branch, on the equivalent healthy system, will be equal to the voltage of CB plus CC. Now, once you start to have the electric field stress increase to a certain level, this could be, for example, due to an overvoltage, or because even at steady state, this is a high voltage as well, then you will start to have an arc here. If this is an arc here, then this will be a short circuit here. Now, this has been disappeared. Remember, the voltage at VCA is equal to, this is KVL, okay, equal to the voltage of CB plus VCC. All of a sudden, you have a short circuit here, then the whole, basically, the whole voltage here becomes equal to 0. So now this is not equal, but you cannot have two parallel circuits with different voltages. So then you will have an arc, an internal arc or a partial discharge happened to make these two voltages now equal to each other. So the increase of the discharge will be dissipated in the form of the partial discharge. So that's this model gives you an idea how to understand the partial discharge. So basically here, if you look to this diagram, and this is the model at the bottom. Now let's look to the dotted line. This is the voltage without discharge. So this is the voltage I am applying here. There is no discharge. Everything is good. Now, if there is a discharge, so the voltage is increasing. Once you have a discharge, it's a short circuit. You will have a sudden drop of the voltage. Now, this sudden drop of the voltage will be accompanied by a sudden increase in the current. This is the current that we are trying to measure. Okay, that is what we call it the partial discharge. So every time there is a sudden drop of the voltage or there is a partial discharge, you will see that you will have a jump of the partial discharge, and this, as you can see, happens in the positive cycle or in the negative cycle. So that is the model, or they call it the capacitive model of the partial discharge. How to measure the partial discharge? There are different methods. One is through capacitive coupling. We measure a voltage drop. Because whenever there is a partial discharge happen, then there will be an electromagnetic field will be produced. So if we have an antenna, then you can detect that partial discharge. Also, because it is the partial discharge, we understand it now as a pulse current, then if we have a current transformer, and that current transformer, basically we use something called Rogowski coil, something that can measure currents with a very high frequency, then we can measure the current. So these are three methods, call them electrical method. But also we can measure the partial discharge using non-electrical methods. For example, acoustic signal. Whenever there is a partial discharge, when it happens, it emits both acoustic and ultrasonic signal. So if we have acoustic signal, acoustic sensor or an ultrasonic sensor, then you can detect the partial discharge. Also, when there's a partial discharge, if it happens in an external system, then you will be an emission of ultraviolet. So if you have a UV camera, and there are two different types of UV cameras. There is one, we use it only at the night. We call them image intensifier. You might have seen them in movies. Basically, the screen becomes like a greenish. So if there's any small light, it magnifies that light so that you can see it. So if there's a small partial discharge on the surface, we use that. And there is something called day corona camera that it can measure the corona during the daytime. Also, if the partial discharge happens in an insulation system like in transformers, then there will be byproduct. Like for example, if you do any gas analysis, you will find that H2 has increased, the level of H2 in the transformer oil. Okay. Now, today we will talk only about the capacitive coupling methods. All other methods, I will talk about them after the term paper. So let's talk about the capacitive detection system. So here we have a high voltage supply. Okay. Now this method is, I want to stress on that you can only apply them at the factory. This is where you have your product, and before you send that product, depends now what type of products. Is this test as a routine test? Because for some assets it's a routine test, for some tests is a special test. So it depends on the assets, but the whole setup is basically under a laboratory, under manufacturer, or even could be an independent laboratory. Now, here we have the high voltage supply. So you apply your high voltage. Actually, there is a filter to take any noise from the signal of the supply. Then you have the CS. CS is the test object. This is what you are testing. And then there is a CK. CK is the coupling capacitor. It couples what happened if there is any discharge happened here. It decoupled here using that capacitor, and then you will have a current here. You have an impedance. You measure the drop here of across the impedance. Take it to measurement system, and that is basically what you measure. Now, how this is in reality look like? This is in circuit. This is how it looks like in reality. So this is the high voltage transformer, which is this. This is where you apply the voltages. This is your test object, which is here your CS. This is your coupling capacitor, which is your CK. And at the bottom here inside, you have the ZM, and you take the measurement from there. Okay. Now, there are advantages and disadvantages of the capacitive detection method or the voltage drop, because you measure it basically as a voltage drop across ZM. This is how you measure the partial discharge, which is basically, it's an electrical method. You have a current, and then you measure the current as a voltage drop. So the advantages is very accurate and very sensitive. You can measure the partial discharge in a few picocoulombs. Okay. Now, we said we are measuring current, but you are telling me that it's a picocoulomb. Coulomb is a charge. As we know that I is nothing but dq by dt. So the charge basically is equal to the integration of the current. So this is what I am measuring. I am measuring the integration of the current pulses. So I have those pulses. I know how long they stay there. Take the integration, then we can find the charge. Also, this system, because it happens in the lab, it is immune to noise. It's not outdoor. It's unlike the other field methods. Then they are basically immune to noise. It's very, very controlled conditions. Now, this test, now on the other side, as a disadvantage, is an intrusive test. Intrusive meaning what? You have to disconnect the asset and connect it to a high voltage supply. You cannot apply this test where the system is energized. So it cannot be done online. It has to be intrusive. You have to send the asset to the factory to do that, or during the manufacturing process, before you send it, you have to do that partial discharge. But if you want to do it in the field, it's very expensive. Okay? Now, so there is a direct connection between the coupling circuit and the high voltage. Okay, so that is make it an intrusive test. It requires an external voltage supply, as I have mentioned. So it is overall, it is a very expensive test, but we do that at the factories or at testing laboratory. We have here a very nice, decent partial discharge measuring system. Also, I will try as well to prepare another video to talk about this partial discharge measurement system. Okay, now, before you do the measurement, you need to calibrate so that you want to know what is the sensitivity of your system. Okay, so basically what you do, you inject a certain current or a certain voltage, a pulsive voltage, through another coupling capacitor of a known value. So you basically you inject a known charge. Once you, because of that, so because you inject a known charge, then you will be able to calibrate it. So I know how much I am injecting in the system. I will see how much I am measuring, and then you can do the calibration if there is any discrepancy between what you are injecting and what we are measuring. Now, this is something extremely important to understand, and sometimes people get confused about that. What we measure what we call the apparent charge, the charge that appear to us at the detector, not the actual charge. What does this basically mean? Okay, to understand that, let's assume I am measuring a partial discharge in a very controlled sample, and let me assume that the void is in the middle. Okay, so you will have a discharge here. Depending on the capacitance of the system that you have, you will have the coupling capacitor, you will have the charge reflected in your detector. Now, if the void changes its position, the overall capacitance will be different. And the amount of a charge released from that defect will be different, because now the coupling capacitor and the capacitor of the system, each time you have a different capacitor. So basically what you see is not the exact charge, but the apparent charge because of the voltage division that you have between the insulation capacitor system and the coupling capacitor is not constant. And we don't know actually where is the location of the discharge inside the insulation system to estimate the capacitance and then estimate the actual charge. So that method is, this is why when you always apply it, you use what we call the apparent charge. Now, how to present this? You apply an AC voltage here, okay? And then the PD will appear superimposed on the sinusoidal. So this is a positive cycle. Okay, here there is no partial discharge, and then it reaches a certain level here, and then you start to see those pulses. Those are the current pulses, and they are showing here superimposed on the AC, so that this is under the rising, and then they disappear. There's no partial discharge when you go to the negative, and then you appear again, and so on and so forth. So this is one way to show it. Okay, another way is the eclipse. So you show them as, sorry, an ellipse like this one. So here, what does this ellipse represent? This represents the positive cycle. This represents the negative cycle. So that figure and that figure is exactly the same, but the way it's looked is different. Now, historically, people like to show it this way. What I noticed recently, people they don't care much now, especially nowadays. You don't have much interference judgment from the workers. Before, you need to put it in that shape to see clearly the pattern of the partial discharge. Now, with the evolving of the machine learning, deep learning, artificial intelligence, there are a lot of artificial intelligence systems that can judge the type of the partial discharge. Okay, so you are now less and less dependent on human beings to tell you these patterns basically represent what type of discharge. And we will talk about one full lecture about the recent applications of machine learning to diagnose the electrical insulation systems. Now, this is a very analog detector. I would say now this becomes history now. It's not really does exist. Most of the detectors now are digital, like this one. And you can save the data. You can basically play with the interference. You can send the results somewhere else. So digital detectors are the norms that we use basically in our PD detection systems. Now, the moment you start to see, now here is this is the positive cycle and this is the negative cycle. The voltage level at which the partial discharge will start to appear, we call it the inception voltage. That is the voltage at which the partial discharge will start to take place. Okay. Now, if the voltage is further increased, depending on the PD source, the PD type, the magnitude, or the frequency of those pulses will increase. Now, when the voltage is reduced to a certain level, and then the PD disappears, we call this is the extinction voltage. So these two terms are very commonly used for partial discharge measurement. The inception voltage, the voltage at which the PD will basically start, and the extinction where the voltage level will start to go down, at which the PD will completely disappear. Now, what I will be doing now, I will show you some different types of control defects, okay, and how they can generate different patterns. But these defects basically are very controlled, means you have one defect at a time. And you can realize that that's not practical when you measure for actual systems. It's much harder to tell the type of partial discharge, especially when you have multiple of sources of partial discharge. But this is at least will give you an idea about if we have a controlled partial discharge, they have basically a controlled pattern. So let's start here. When we have a sharp point, okay, sharp point meaning it's corona. So this is a partial discharge coming from corona. Then we have what we call the threshold pulses. Threshold pulses, and you see them in the negative cycle. You don't see much in the positive cycle. Now, when you increase the voltage, then the number of pulses will increase. So those pulses will increase, but their magnitude will not increase. Now, there is an explanation why this is happening, but this is covered in another course, the dielectric course, where we talk about the phenomena of discharge and why the threshold pulses happened only at the negative, and why when you increase the voltage magnitude, their frequency will increase, but their magnitude will not increase. Then this is when we have a void. Now, when you have a void here, and this void, let's say, assume it is in the middle, and this void is inside the cable, then the discharge will start before the crest, before the peak of the voltage, once it exceeds the inception voltage. And then if the void was in the center, then you will see that the partial discharge in the positive cycle and the negative cycle are happening almost the same. So you see like a sort of more of symmetric. So here in the positive, start at the partial started here, then disappear, and then started there. So it happens at the same voltage level. Now, if it is basically close to the high voltage or close to the low voltage, then you will not have such symmetry between the two discharges. Now, what if we have multiple cavities, not just single cavity, but multiple cavities? It means that the partial discharge maybe happen here, then happen there, maybe happen here and there at the same time. So you will have sort of random voids. This is, for example, if you are degassing a transformers, when you fill the transformer with oil, we want to prevent any bubbles inside the transformer to degas it. If you don't have a very effective degassing, then you have a lot of air bubbles. Then you will have this scenario. Now, this one basically, once you have this, once the partial happen, the bubbles will disappear. Because you will burst those bubbles and then no problem. But if this is happening, for example, curing for an epoxy material, and because the curing was done badly, then you will have multiple voids inside and you will have this, and this would be persisting. Now, as you can see here, there's no actually a clear pattern between the two. This is very, very sort of random because the partial discharge happened at different times between those different cavities. Now, similar behavior we have here. If we have two conductors, both are insulating. Okay, so this is one conductor, this is another, and you start to have discharge here on the surface. Now, this could be due to, for example, contamination on the surface here or weak insulation system. When you start to have this, again, that will be having a very similar random behavior compared to the previous one. Now, gas bubbles, as I mentioned, the cavities, gas bubbles, they are very sort of similar to each other here. So again, you see this random point. The difference, as I mentioned, between the bubbles and the cavities, if they are permanent cavities, then the bubbles will disappear. So then you will see a clean ellipse that doesn't have any partial discharge superimposed on it. And this is why it's very important to measure the partial discharge in a transformer before it leaves the premises. I remember a story in Canada, without mentioning names, one of the big well-known manufacturer, they were actually making phase shift transformers. Those phase shift transformers, we do them to block the power. Okay, so if you want to control the real power flow, you control the angle between one point to another. The real power goes from the voltage with a higher angle to the voltage with a lower angle. So if you can change the phase shift, you can block the power. So there was a need for, this has happened, by the way, maybe around 20 years ago when I was doing my PhD. So there was a need for Hydro One at that time. They wanted, or Ontario Hydro, they want to do a phase shifting. So they asked this manufacturer to do that. And I know the story because I know a friend of mine was working with this company. Then they go there and they measure the partial discharge, and they found the partial discharge higher than the acceptable level. Okay, so they thought that this is maybe normal because of there is some the transformer size is much larger, so they don't have previous experience that with this size of transformers, what is the baseline level of the partial discharge. So they let it go, okay, and they ship the transformer to the site. Few days or weeks, I don't remember, the transformer completely exploded. The transformer was a huge transformer. I have seen, because they made two units, twin units. I saw the second one. It's a very, very large transformer filled with oil, and we know now transformer oil is flammable. So you can imagine how devastating was the situation. So the utility asked the manufacturer to go and check the second transformer before they ship the transformer. They measured the partial discharge. They found that it was the same level as the one that is failed at the site, which is something really bad. Then he told them, never ship the transformer until you really know what is going on. Okay, so they tried for 6 months. They asked I remember it's a funny story. One of the experts from the US told them that I will spend one day, and he charged them thousands of dollars. And he told them that, but there is no guarantee for the results. I will come, you pay me, no guarantee. Came, did the inspection. He used ultrasonic sensors, if I remember correctly. he couldn't find what is or where is the source of the partial discharge of the transformer, got the money and left. He brought experts from the company research centers, nothing. Then they have to open the transformer. And opening a huge transformer like that and dismantle it is a nightmare because it's a lot of loss. Then when they opened the transformer, they found that the cause of the partial discharge was sharp points. The workers somehow they forgot to, because you cannot leave any sharp point inside any insulation system, because this sharp point will generate very high discharge electric field at the tip, and this will be a partial discharge. And having the insulation system, this will damage the insulation system. So they were measuring the partial discharge. They thought that is something like this, maybe air void or air bubble, sorry, or something very because of the transformer size is large. Then they ignored it, and the end of the story, that manufacturing premises, I think because of that incident, they have to shut down. Okay, now there are some other types of interferences. Now, sometimes you don't measure a partial discharge, but you measure an interference from the lab. Okay, so for example, if you have a small discharge happened, now if you have a small discharge take place at both the positive and the negative before the crest, this means maybe sometimes there is no good contact at your variac. Now the partial discharge is not coming from your sample, it's coming from your setup. Okay, so here the partial discharge happened because of you have a loose contact, your variac, you increase the voltage. So at the beginning, you start to get something. Usually you get the partial discharge when you come close to the inception of the partial discharge, not at the zero crossing here. When you have the partial discharge at the zero crossing, it means that there could be something else. It's not the sample, it is the system which generates the partial discharge. So this is a contact noise interference. Sometimes you have a tool around it close to the high voltage. It induces a partial discharge, and it is random. And here it is like if you have a floating metallic object, you will see the partial discharge happen like that. This has nothing to do again with the insulation system. So that is also basically is a noise. Okay, so this is, as you can see here, these are controlled samples. There is noise. There is some problems can happen. So the patterns are not easy to do. You need an expert to be able to tell you what is actually the source of the partial discharge. What is the type of partial discharge? As I mentioned, now people are trying to use artificial intelligence system, not to rely much on the expert opinion, but to rely more on the expert idea, or sorry, the machine learning, the expert system decision. Now, let me talk about a little bit about partial discharge measurement of an actual assets. All I mentioned before was basically just the partial discharge for controlled samples. Now, let me talk about for distribution transformer, just an example, and for every test or for every asset, you will have a standard, you have a way to do the measurement of the partial discharge. So as per the IEC standard 60076-3, the partial discharge for distribution transformer is a special test. We mentioned about routine, type, and special test. Special test, this is a mutual agreement between the manufacturer and the supplier, and the customer, if we want to do that test. And usually it's done with a higher cost. Now, for power transformers and for even dry type transformer, this could be a routine test. Now, what is the criteria or how the test is done? If you remember, we have two different types of testing of transformer. We have the hypo test, or the separate source voltage test, where you apply the high voltage, for example, after you short circuit the high voltage 3 phases, and you short circuit the low voltage and you connect it to the tank, and you apply the high voltage at the high voltage terminals, and basically you are measuring the integrity of the insulation between the high voltage and the low voltage, or the high voltage and the ground. We call this is testing of the clearance. But also we have the induced voltage test, where you apply high voltage to the three phases at a higher frequency, and then you induce the voltage in the low voltage side. Now, for the partial discharge, both modes are used, but the induced mode are used much more. So this is the circuit here. You have the generator, you have a transformer. So that is the testing system. This is your testing. You testing setup. You have a generator and you have a transformer. This is the transformer that you are testing for partial discharge. Here, this is the filtering to filter anything coming from the system that will not cause any partial discharge. So here you are connecting the three phases. So that is in the induced mode. This is just a potential transformer to measure the applied voltage. And here is the ZM, the shunt impedances through which we want to measure the partial discharge. Now, there are acceptance criteria for oil-filled power and distribution transformers. At 130 of the rated voltage, it should be less than 300 picocoulomb. At 150%, it should be less than 500 picocoulomb. Now, for the cast resin transformers, which is dry type transformer, it's much less than that, because when you have this type of partial discharge in the transformer and it's oil filled, oil, whenever there's a partial discharge, as I said, when there is bubbles disappear, the partial discharge will disappear. But for a cast resin or epoxy type of transformers, if you have a partial discharge inside the installation, it will start to eat the installation system with time until you have a complete failure. This is why the tolerance here for dry type transformer is much less than the oil field transformer. So finally, the final comments here, PD under the controlled conditions is very complex patterns have here, very difficult to interpret. I showed to you just single sample of partial discharge control. Now, what if I have a transformer? You could have 3 or 4 different sources of partial discharge at the same time. So it's not really easy to interpret those partial discharge. Add to that, now there is a scarcity of experts in the power system testing environment. There's not many as it used to be in the 70s, early 80s. Now, those experts, people, they are not available. It's very hard to find them. And this is why we were trying to find the expert systems, which is the machine intelligence systems, which has to be built by expert as well, because it depends how you train those models. We'll see that, we'll talk about that later on. You will have good or bad judgment system. You need to have a good knowledge about the system that you are measuring, the installation system that you have. And also another important thing is the trend over time. Maybe certain pattern at certain time doesn't really important, but with time, do we have an increase in the partial discharge or it is stabilized? Sometimes that is good enough. Sometimes when, for example, you energize a transformer, there is a sudden increase in the hydrogen level, which is an indication of partial discharge, and then it stabilizes, it disappears. Okay, so that's not really an indication of a failure in the system. Again, these things comes with the experience that you have to be able to judge the your installation system. Okay, I will stop the recording.